One of the greatest problems in the world right now is gaining access to clean water. Fresh water sustains human life and is vital for human health. It is estimated that about 1 in 10 people do not have access to clean water, which is approximately 800 million people in the world. As a result, contaminated water causes roughly 7 million deaths a year. However, reverse osmosis and forward osmosis may be the solution to this problem.
Water purification via semi-permeable membranes facilitate the separation of salts and minerals in water sources, such as seawater, producing clean, potable water. Membrane distillation utilizes the colligative property, osmotic pressure, as a driving force for water diffusion through the membranes while retaining brine. Osmotic pressure is defined as the pressure required to prevent the inflow of the pure solvent in solution across the semi-permeable membrane. Membrane distillation methods are preferable over other desalination techniques because it does not require heating and evaporating the bulk water source, an energy-intensive process. Two established methods for membrane water purification are forward osmosis and reverse osmosis.
In a forward osmosis system, water flows from the feed solution into the draw solution due to a difference in osmotic pressure. Water flows naturally from an area of low osmotic pressure in the feed solution to an area of high osmotic pressure in the draw solution in an attempt to balance out the change in pressure. Osmotic pressure is itself a colligative property dependent upon the concentration of solute in the solutions.
In the reverse osmosis system, an external energy source pressurizes the saltwater solution in the bulk feed, overcoming the osmotic pressure of the system and forcing water through the semi-permeable membrane while retaining salt. The desalinated water passes on as the permeate, and the remaining concentrated salt-water solution leaves the cell as the retentate. The water flux quantifies the amount of water that traverses the membrane as seen from the following equation.
Before beginning the experiment, a calibration curve must first be created in order to determine the amount of salt present in the solution with respect to its conductivity.
In order to begin performing forward osmosis, a few steps must first be taken in order to set up the experiment. First, begin by turning on the chiller to the desired temperature, and then filling the feed and draw tanks with 2 liters of distilled water each. Next, add a stir bar to the feed solution to facilitate mixing and turn on the mixing apparatus. Then, wet the main cell with distilled water. Then, trim the membrane to the proper size and load it into the main cell while maintaining proper orientation. Then you must secure both halves of the cell by attaching the nuts and tightening them with a wrench. Now open the Excel document and prepare the software to begin taking data points every 60 seconds. The pumps must then be turned on and given enough time for the flow rates to level out. Both pumps must be operating at the same flow rate for the experiment. Now you're ready to begin taking data points with the software. Once the weight of the draw solution maintains a constant weight, you can begin to add the salt solution in order to begin concentrating the mixture. While this is going on, make sure to take readings of the draw solution with the conductivity probe every minute. Once the weight converges after the addition of the salt solution, concentrate the mixture again with more salt solution and repeat as necessary for each desired molar concentration. Also make sure that the flow rates are still equal in order to ensure accuracy within your test results. Begin breaking down the experiment by emptying out the feed and draw tanks into a bucket, which you will then pour down the sink. Make sure not to throw away the stir bar. Then fill the system with DI water and run it for another 15 minutes. Once finished, you may then pour out the water. Now that the tanks are empty, you may begin air purging the system. Turn on the pumps, making sure that flow rates have been given enough time to level out.
First, turn on the chiller and set the temperature between 19.3 and 19.8 degrees Celsius. Fill the feed tank with 9 liters of DI water. Each cell must be wetted with DI water before the addition of the membranes. Load the selected membrane into each cell, cutting it to fit the cell if needed. The shiny side of the membrane should be facing the more concentrated side of the cell. Secure the membrane with washers, nuts, and bolts. Each cell should be tightened with a wrench. The permeate tubing should be placed in a waste beaker. Make sure the bypass valve is in the correct position and start the pump, making sure the frequency is set to 15. Allow all air bubbles to purge from the system, and set the desired flow rate, ensuring the flow rate is below 2 liters per minute. Start off by weighing 3 graduated cylinders, both dry and slightly wetted. Add a 1 liter 2000 part per million NaCl solution to the feed tank. Set the desired pressure for the system, ensuring the pressure is below 350 psi, and allow 10 to 15 minutes for the RO system to equilibrate. Collect the desired volume of the outlet permeate from each cell and record the collection time. Weigh the graduated cylinders and use the probe, making sure the 2 metal bands are submerged in solution to record the conductivity of all 3 cylinders. Then dump the water back into the feed tank. Remember to periodically take conductivity and temperature measurements of the feed tank as well. Repeat these steps at varying pressures, flow rates, and membrane types for the system. Turn off the pump and chiller and drain out the feed tank by opening the bottom valve. Fill the feed tank with 10 liters of tap water and run the RO system for 5 to 10 minutes. Drain out the feed tank again. Repeat this process again with tap water, and then finally with DI water. Open the bypass valve so that the RO system is connected with the air purge line. Using a compressed tank of air, flow a low amount of air pressure, below 200 psi, through the setup, making sure not to fully connect the fittings. Open each cell and remove the membranes. They can be safely disposed of after examining them for defects.
Before the experimental data can be addressed, it must first be noted that the salt solution was added not to the draw solution, but to the feed solution. This had the effect of making many of our calculated flux values negative, which were also affected by the fact that the membrane is oriented upside down. Membrane permeability was found by finding the slope of water flux versus effective concentration and effective osmotic pressure. Salt permeability was found by finding the slope of salt flux versus change in effective concentration. It was found that as flow rate was increased, water flux and salt permeability also increased.
For reverse osmosis, the change in mass collected from the permeate of each cell allowed for the calculation of water flux. Pure water solutions were run through the RO system to obtain these results. The transmembrane pressure is the difference in the transmembrane hydraulic pressure gradient and the effective transmembrane osmotic pressure gradient. The water flux was plotted as a function of transmembrane pressure. The reported slopes are the hydraulic permeability constants for each membrane. The lines are forced through the origin since there is no intercept coefficient in the water flux equation shown here. Further analysis on the salt flux through the semi-permeable membrane was obtained from the conductivity readings collected during the saltwater trials. The governing equation for salt flux is displayed. The salt flux was plotted against the effective concentration gradient. The slopes of the lines represent the solute permeability constant for each membrane. These lines are also forced through the origin. To quantify the separation effectiveness, salt rejection was calculated at varying pressures. The observed salt rejection and the intrinsic salt rejection at the membrane was considered for each tested semi-permeable membrane. Our results ranged from 57% to 93% salt rejection. The concentration polarization was also investigated. The concentration polarization of the membrane impacts the pressure required for the diffusion of water through the membrane to occur. Concentration at the membrane on the feed side of the membrane is larger than the observed concentration gradient. This is proportional with a larger osmotic pressure gradient needed to be overcome for the water flux to occur, meaning more power needs to be supplied to the pump to meet the pressure output.
Over the course of the experiment, it was found that changes in flow rates had a marked effect on the fluxes. Both water and salt permeability increased with the increase in flow rate. It was also found that increases in salt concentration had the exact same effects.
From the data collected for reverse osmosis, varying the pressure increased the water flux and salt flux through the semi-permeable membrane. This finding was intuitive, as a greater pressure on the feed stream should cause a greater driving force for diffusion of water and salt through the membrane. We observed that the BW30 membrane provided the largest salt rejection, and therefore the best separation of minerals from the bulk water feed. However, NF270 did provide the highest water flux, while also allowing more salt to diffuse through the membrane. Unexpectedly, salt rejection increased with increased pressure. This does not agree with the literature, as the exact opposite should be observed. The experiment should be revisited to understand the error that occurred.